Continuing on the review for exam 3, more content that we discussed. Another topic that we discussed is the relationship between the charge on the capacitor. This is a parallel plate capacitor. Relationship between the charge on the capacitor and the voltage drop across the capacitor. So when I say a charge on a capacitor of charge Q, that means one side of the capacitor has a charge plus Q and the other side has a charge minus Q, as you can see in this picture. And the relationship between them is Q is equal to C times V, where C is the capacitance of the of the capacitor, and V is the voltage drop across the capacitor. Alright, so if there's a voltage of 9 volts across a capacitor of 100 microfarads, the charge is simply the product of 9 volts and 100 microfarads, which is 900 microcoulombs. That one plate would have plus 900 microcoulombs, the other plate would have minus 900 microcoulombs. That's what's meant by that. Another thing we discussed was equivalent capacitance. If you have capacitors that are in series, C1, C2, that the equivalent capacitance, if you could replace these two capacitors with just one capacitor, that capacitor would have a value of 1 over C1 plus 1 over C2. It's the same as equation as when you have a parallel resistor, is when you have series capacitors. All right? The other equivalent capacitance we discussed was parallel capacitance, and we did this in lab as well, both series and parallel. If you remember me with aluminum foil and the capacitance meter, trying to show this. The equivalent capacitance in this case is simply the sum of the two capacitances when they're in parallel. Then you could actually have combined series parallel circuits. For instance, what if you had two in parallel here and then one in series here? Whoop. And I wanted to know the equivalent capacitance of this arrangement. Okay, so let's say this is C1, C2, C3. What I would do with that is I would do the same thing I did with resistors. I would combine the ones that are parallel and say, okay, this is like another capacitor whose value, you call it C4 if you want, but it's the parallel combination of these two, which is C1 plus C2. And then I'd have to use the series equation to say that the combination of these two in series is 1 over the quantity C1 plus C2 plus 1 over C3, the inverse of that. I'll write that out right here in what space I have. So it would be this, 1 over C1 plus C2 plus 1 over C3. All right, so these are all in the denominator. Then you take the inverse of it. And that would give the equivalent capacitance of this combination right here. Then we discussed and had a lab on RC circuits. And the main thing for RC circuits, just as a review, is if you have a resistor and a capacitor. And by the way, those of you who are biology students or interested in biological processes, our nerve impulses, the time at which it takes a nerve impulse to get from one part of our body to another, is governed by the RC time constant associated with the capacitance of our neurons and the resistance associated with the neurons. So this is actually very relevant for biology as well. Remember, we are a lot of electrical impulses passing around us through our nerve cells, controlling a lot of functions. Some combination of chemical and biological signaling chemical and electrical signaling is what's part of what is governing our behaviors and our survival, even at the cellular level. So what happens here is when you have a capacitor of a certain voltage across it, it's going to, the charge is going to drain through this resistor until the whole thing is neutral and both plates will have zero charge on them. And the process for that is, if you have an initial voltage across the capacitor, I'll call it VI, and you want to know what the voltage is at some time, it's equal to the initial voltage times e to the minus t divided by RC. That is the equation. You can use that and solve for any of these quantities, and on the quiz, take a look at that, because I do that. I do it using this equation. But when V of t is equal to 0.37, or about 37% of the initial voltage, that's a really special time. At that time, this exponent of e is e to the minus 1. So that means that t is equal to RC. When this is true, t is equal to RC. So you have a really simple equation to calculate the relationship between t, r, and c. So if you want to find t, you multiply r times c if you know the two of them. And that t will give you the time at which the voltage is 37% of the initial voltage. Or you can calculate c and r if you know t in one of these here. That's the RC circuit. Then we talked about magnetic fields, and I do recommend taking a look at the videos where I discuss magnetic fields, where I explain that they come from basically electrical currents, or what generate magnetic fields. Unlike electric charges, which can have both positive and negative, magnetic fields can't have a single pole, a north or a south pole. They come in pairs. You always have a north and a south pole together. You don't just have a north pole or just a south pole, whereas you could have a positive or a negative charge by itself. But these are very different. Now they're related in the sense that when you have moving charges, like through a wire, and you have a current, which is what a moving charge is, that generates a magnetic field. And you can find the magnetic field, its direction and its strength. Its strength is given for a wire by B is equal to mu 0 I over 2 pi r. That's the equation for the magnetic field associated with a wire some distance away from the wire, where this is r. So when r doubles, the magnetic field is only a quarter as strong, because it's an inverse r relationship there. I'm sorry, when r doubles, the magnetic field is half as strong. That's what I meant to say. When r doubles, the magnetic field is half as strong because you're twice as far away. And the magnetic field increases as your current gets bigger. Of course, that makes sense. And mu 0 is known as the permeability of free space. So it's 4 pi times 10 to the minus 7th. And its units are Tesla meters per amp. There's a bunch of units you can use for it. And you actually calculated that in one of your labs using solenoids, which I'll mention in a minute. So this is the strength of the magnetic fields, different distances away from a current I in a wire. The direction of the magnetic field is determined by using the right-hand rule. Remember, the magnetic field wraps around currents, so there'd be donuts of magnetic field around this current passing through this wire. And using the right-hand rule, putting my thumb in the direction of the current, my fingers show you the direction of the magnetic field, how they'll wrap around the wire. Up top here, the magnetic field is going to come out of the page, and down below it's going to be into the page. And it gets weaker as you get further away from it. All right? So that's a magnetic field associated with a wire. And magnetic fields associated with solenoids is the other thing we talked about, and that's where we did the lab. Solenoid, remember, is a coil of wires. And if there's a given length here, let's say this length is equal to 50 centimeters, or 0.5 meters. We're interested in the number of coils per meter, or per unit length. So if this is half a meter and I count 1, 2, 3, 4, 5, 6 coils, I would say that there's 12 coils per meter here, because there's 6 coils in a half meter. So I have to double that, and I'd get 12 coils per meter. That would be little n. And the magnetic field within the solenoid is given by mu 0 n times I. The more coils you have, the stronger the magnetic field. The bigger the current you have, the stronger the magnetic field. And the direction of the magnetic field is given by the right-hand rule. You put your fingers, in this case, in the direction that the current is flowing through the coils, whether it's this way or that way. The magnetic field will be directed either that way or that way through the coils. And what's interesting and useful about a solenoid is it provides a homogeneous magnetic field. That means it's the same value anywhere inside the solenoid. Has the same value here as it does here. Same value everywhere inside there. I think I'll stop this video and I'll do one more after this to complete the review for exam 3.